Okay, we're going to go over instantaneous rate of change. So here's our little initialism. Again, IRC is our instantaneous rate of change. And this is a bit different from the formula we use for average rate of change. And we're going to talk about how we get to this formula here. Okay, but this is still the same idea of essentially a y2 minus a y1 over an h value. And an h value is a number that is extremely close to 0, but is not exactly 0. Because we cannot divide by 0, you'll end up with an error on your calculator. There's lots of videos from other smarter math teachers than me talking about why you can't divide by 0, okay? So if you want to know, look at theirs. But so this is essentially average rate of change, and we're going to talk about it. We're going to show you how we get to this formula using our information from the last lesson. So it says the volume of a cubic crystal can be modeled by the volume being a variable of x. X is going to be one of the side lengths. I just didn't write it into the question. Okay, and this is essentially x to the power of 3. So it's a cubic function. We're going to estimate the instantaneous rate of change in the crystal's volume at a side length of 5 centimeters. So what we're looking at, and here's just kind of a rough sketch, we're going to have a cubic function, okay? So it goes something like this. And at 5 centimeter side length, we really want to find the slope of a line that would be tangent to this curve at that point, okay? And the reason we're only looking at one point and we can't use the slope from before is because for average rate of change or your, slope of a linear line, we need 2 points. But we want it to be instantaneous. Instantaneous would mean only 1 point. So that's why we have to build a new formula in order to figure this out. So what we're going to do is we're going to use our old formula to start off, and then we're going to kind of build into the next one. So our instantaneous rate of change here, at 5 seconds, let's plug it into our formula. So our volume at 5, okay, is equal to 5 cubed. Who knows it? 125. Excellent. Okay, so that would be essentially be our first coordinate that we're going to plug in. So we have the side length being 5 and our volume of the cube going to be 125. Now our other value is we're going to use an x value that is extremely close to the number 5. So let's say volume at, what have they given us here? We could use volume at like 4.9, okay, which essentially gives you 4.9 cubed. And I've built something over here to solve that quickly for us. So 4.9 cubed is roughly 117.649. Okay? 117.649. So again, we have another point, which is very, very close, but not exact. So, sorry, I wrote instantaneous rate of change, but I'm going to change that to, we're going to use the average rate of change for this same idea. Okay? And if you remember from average rate of change, we take the y value or the f at x value of one of them. We'll start with our green one here. We'll call this our x2 and our f at x2, or technically should be v at x there because we're dealing with volume, and our x1, and we'll call this v at x1. Okay, change that to a v. There we go. So we're going to take our first value, which is 117.649, and we're going to subtract from 125. Didn't leave myself a lot of room here. And we're going to be dividing by 4.9, subtract our value of 5. Okay, so let's move this down so we can work on it a bit. I know you can't do that on your note page. I apologize. Okay. So let's figure out these values as close as possible as we can. Okay. So 117.649 subtract 125. Okay. And actually, I think I can bracket all that. And it's going to be divided by 4.9 subtract 5. And it gives us a slope. And if anyone wants to test, that sound right to you? Okay, I guess so. 73.51. 73.51. Okay. Value that was relatively close to 5, right? That was 4.9. It seems pretty close, but we can get much closer than that. Okay. Let's now go with the same idea, but let's use a value even closer. So we'd have 5 and 125. That's going to be a constant for us. And this time, our other coordinate will be 4.99. okay? And we need to figure out whatever that y value is. And on the other page, I've just quickly built something into the computer that'll solve it for us quickly, so we don't have to spend too much time on that. Okay, so at 4.99, the y value would be 124.25. It's all right there. And then the computer solved the next step for us. Okay, here's our average rate of change formula. So this is telling us the slope is now 74.85. So let's talk about that. The new average rate of change is 74.85. Information, okay? As our x value gets closer and closer to our number 5, what do you think our slope is probably going to approach by just looking?
75.
Yeah, it's probably going to end up at 75, this slope, okay? And that's going to bring us to the idea of using this formula here, okay? So we're going to do the same thing. Now we're going to use this other formula. And h is going to represent a value very, very close to 0 in this case. So let's do the formula we started with, our instantaneous rate of change, okay? And if we look above again, that was written as, how do we have it written here? A plus h. Okay, so f at a plus h, subtract our f at a value, all divided by h. Okay. And our a value, in this case, is going to be our value of 5. We're trying to find the instantaneous rate of change at 5. Okay, and h represents a number that is approximately 0. Okay, but it's technically a little larger, again, because we can't divide by 0. So we're going to actually plug in a value that we think is very, very close to this. Now our f at, and actually let's look at our f at a first. F at a, okay, is our x cubed. That's what our function is that we're working with. Okay, so when our a value is 5, our f at a is going to be obviously 125. And we can write it, and this is what's important. I'm going to write it like this, 5 cubed. So I'm not going to solve it. I'm actually going to just plug that, 5 cubed. Okay, we're going to plug that in for our f at a. From there, our other formula would be f at a plus h. Okay, that would be our 5 value again, plus h this time. We haven't chosen a value for h yet, cubed. Okay? And same idea, let's do that in blue. We're going to plug this value in for this part of the equation here. Okay? And h, we still don't know what it's going to be, so we're gonna choose that after. So we end up with our bracket 5 plus h cubed minus 5 cubed, all divided by h. Okay, and the reason I wanted to write it this way is I wanted to show you guys that these are essentially the same thing, but we're going to choose a value. In this case, we're going to choose a value for h that is an extremely small number, so that we're very, very close to almost the instantaneous rate of change. So before we used 4.99, so that's a difference of 0.01. Okay, let's use an h value that's even closer. Let's go with h being 0.0001. Okay, the h value is the difference in our two x values. Okay, so we're going to replace our h with that number. So that means we would get 5 plus 0.00. How many zeros did I write? 3. There you go. 1 cubed. We know this will be 125, and our h value below 0.0001. Okay. Essentially, this gives us 2 cubed minus 125, all divided by 0.0001. Okay. And we're going to type this into our calculator, and this will give us a slope again, hopefully even closer to 75 than before. So we have bracket 5.123 cubed, okay, subtract 125, and all of that is going to be divided by 0.0001, and lo and behold, we get 75.0015. It's essentially, or we're going to say approximately, the value of 75, just as we estimated before. Okay, so this formula builds on our average rate of change, except that it finds values that are extremely close to each other.